Hey guys, my name is Chinmay Srivastava and I am a second year student of Bennett University doing my Bachelor's of Technology in Computer Science. And today I am going to tell you about change problem using dynamic programming. Before recording this lecture, I stopped by the coffee shop and as soon as I gave $5 to the cashier, she faced an algorithmic problem of which coins to choose to give me the change. And cashiers all over the world use an algorithmic approach called greedy algorithm to solve this problem. Today we'll learn how cashiers and computer scientists use greedy algorithm for solving many practical problems. So the change problem is finding the minimum number of coins needed to make change. More formally, input to the problem is integer money and positive integers coin 1, coin 2, coin D that represents coin denominations. For example, in the US, coin 1 will be 1 cent, coin 2 will be 5 cents, 10 cents, 25 cents and 50 cents. And the input is the minimum number of coins with denominations coin 1, coin 2, coin D that changes money exactly. So today in the morning, when cashier had to return me 40 cents, she most likely used the following algorithm. First, finding the largest coin denomination that is smaller than 40 cents, it will be 25 cents. So she gave me 25 cents, 15 cents left, and then the next challenge is how to change 15 cents. The next step is she probably found the largest coin smaller than 15 cents. It is 10 cents. She gave me 10 cents and finally she returned 5 cents. As a result, she changed 40 cents as 25 plus 10 plus 5. Do you think it's the minimum number of coins she could possibly return? It is the minimum number of coins in the United States. But if you travel to Tanzania, it won't be the minimum number of coins because there is a 20-cent coin in Tanzania. And therefore, this greedy approach to solving the change problem will fail in Tanzania because there is a better way to change 40 cents, simply as 20 cents plus 20 cents, using Tanzanian 20 cents coin. Since the greedy approach to solving the change problem failed, let's try something different. Let's try the recursive algorithm for solving the same problem. Suppose we want to change 9 cents and our denominations are 1 cent, 5 cents and 6 cents. What would be the optimal way to change 9 cents? Well, if we only knew what is the optimal ways to change 9 minus 6 cents, 9 minus 5 cents and 9 minus 1 cent, then we would know what is the optimal way to change 9 cents. In other words, to change 9 cents, we need to know how to change small number of cents, in our case 3 cents, 4 cents and 8 cents. Therefore, an approach to solving this problem would be to use this recurrence to write this recursive program. This idea is implemented in the program recursive change. To change money, cents using coins, coin 1, coin 2, coin D, we do the following. We first recursively call recursive change with the amount of money, money minus coin 1, money minus coin 2 and money minus coin T, and thus find minimum number of money for these D choices. We have plus 1 coins, there is one more coin to add and returns this way. This looks like the right approach to solve the problem, but let's check how fast the resulting program is. So when we're changing 76 coins, there are actually 3 choices. We need to recursively call recursive change for 70 cents, 71 cents and 75 cents, but for each of these values we need once again to call these 3 choices. And we will continue growing this tree and very quickly it will turn into a gigantic tree. Let's check how many times we have already tried to change 70 cents. 3 times. and we only started expanding this tree. In fact, if we continue further, we will see that there were 4 times when we needed to compute recursive change for 70. How many times do you think we will need to run recursive calls when we compute the minimum number of coins for 30 cents? It turns out that we will need to call it trillions of times, which means that a seemingly very elegant recursive change program will not finish before the end of your lifetime. So as simple as the change problem looks, neither a greedy approach nor a recursive approach solve it in a reasonable time. 60 years ago, a brilliant mathematician, Richard Bellman, had a different idea. Wouldn't it be nice to know all the answers for changing money minus coin I by the time we need to compute an optimal way of changing money? And instead of the time-consuming calls to recursive change money minus coin I that may require to be repeated trillions of times, they would simply look up these values. This idea resulted in dynamic programming approach that is applied in thousands of diverse practical applications in a myriad of different fields. And the next idea of dynamic programming is to start filling this matrix, not from the right to the left as we did in the recursive change, but instead from the left to the right. So we will first ask the trivial question, what is the minimum number of coins needed to change 0 cents? And of course it is 0. What is the minimum number of coins to change 1 cent? Obviously it is 1. But we can compute this number by finding what is the minimum number of coins to change 0 cents and adding 1 coin. We will proceed in similar fashion to compute the minimum number of coins to change 2 cents, 3 cents and 4 cents. There is only one possibility to derive this problem from the previous number. And for 5 cents, actually there are two possibilities, green and blue. For green one, you can derive it from 0 cents by adding 5 coins, and for blue possibility, we can derive it from 4 cents by adding 1 penny. Well, which possibility would you select? Of course, the one that gives you the minimum change for 5 coins. And continue further and apply the code to 6 cents, and there are 3 possibilities, and once again we need the optimal choice that correspond to minimum number of coins, and let's say it may be 0 coins plus 6 coins. We continue for 7 cents and continue for 8 cents, and finally very quickly we actually found the correct for 9 cents. We need 4 coins to change 9 cents. And this results in DP change algorithm that simply fills up the table that I just showed you from left to right. You may be wondering, why is this algorithm called dynamic programming and what does it have to do with programming? Well, in fact, dynamic programming has nothing to do with programming. Amazingly enough, dynamic programming is one of the most practical algorithms computer scientists use. But when Richard Bellman was developing this idea for Air Force project, he was working on it. It looked completely impractical, and he wanted to hide that he is really doing mathematics from Secretary of Defense. Rather than working on Air Force project, therefore he invented a game that basically has nothing to do with what dynamic programming algorithms do. In his own word, he said, what name could I choose? I was interested in planning, but planning is not a good word for various reasons. I decided, therefore, to use the word programming, and I wanted to get across the idea that this was dynamic. It was something not even a congressman could object.